To understand the plasma universe theory, we first need to know about plasma. Besides the common states of matter, solid, liquid, and gas, there's a special state called plasma. Plasma occurs when matter is excited to a highly unstable state, allowing the electrons within to move almost freely, creating a high-energy state. A familiar example of plasma is lightning, which is the result of a part of the atmosphere entering the plasma state. In the plasma universe theory, the universe is seen as a vast ocean of plasma, filled with unevenly distributed Birkeland currents, which are why the sun can produce energy. This unique view of the universe is closely associated with two distinguished scientists, Hans Alfvén, a Swedish scientist who won the Nobel Prize in Physics in 1970, and Kristian Birkeland, a Norwegian scientist who, despite not winning a Nobel Prize, was highly respected and nominated 7 times. Birkeland focused on studying the Earth's auroras, concluding that the auroras were not only caused by solar wind but also by charged particles from other parts of the universe, leading to the concept of Birkeland currents. How does the plasma universe theory explain the sun's energy production? According to the theory, the universe is filled with unevenly distributed Birkeland currents, or more precisely, scattered charged particles. These negatively charged, weak and dispersed particles can be attracted by positively charged bodies like the Sun and Earth through their gravity and electrical potential difference. Earth, being smaller, attracts limited Birkeland currents. However, the Sun, due to its large volume and strong gravity and electrical potential difference, can attract more Birkeland currents. As the Sun moves at high speed in the galaxy, it attracts a far greater number of Birkeland currents than Earth, creating a natural supercapacitor between its positively charged core and its atmosphere. This interaction between the large amounts of negatively charged Birkeland currents creates the Sun's energy. As the Birkeland currents increase, the Sun's atmosphere is eventually penetrated by massive cosmic currents, creating cosmic-scale lightning that stretches tens of millions of kilometers. These lightning events, constantly fueled by the Birkeland currents from the universe, cover the Sun's surface and continuously bombard its atmosphere, turning the Sun into a giant plasma sphere. The energy we observe from the Sun, including light, actually comes from the radiation released by these plasma formations. This explains why solar flares and solar wind are so unusual. From the perspective of the plasma universe theory, solar flares are caused by the Sun suddenly encountering dense Birkeland currents, leading to atmospheric penetration. Since flares are plasma formations created by this penetration, their temperature is much higher than the surrounding solar atmosphere, similar to how the temperature inside a lightning bolt far exceeds the surrounding air. Similarly, the phenomenon of solar wind is not considered unusual in the plasma universe theory. These charged particle storms move quickly along the paths of Birkeland currents in the universe, explaining the unusual speeds of solar wind. Some skepticism towards the plasma universe theory suggests that radiation alone might not account for the level of energy received by Earth. In other words, if the Sun were not hot enough, Earth couldn't stay warm. This can be simply tested by comparing how a microwave oven heats water to 100 degrees, but the components generating microwaves remain cooler, thus exploring the viability of the plasma universe theory. The Zan effect provides another clue supporting the plasma universe theory. In 1896, Dutch physicist Peter Zeeman discovered that magnetic fields can affect atomic spectra. Together with his mentor, Hendrik Lorentz, they studied the effect of magnetic fields on spectra, naming this phenomenon the Zan effect. For this discovery, they won the Nobel Prize in Physics in 1902. Further research found the splitting of atomic spectra in magnetic fields to be complex, known as the anomalous Zan effect. By studying the interaction between magnetic fields and atomic spectra, scientists can calculate changes in magnetic fields based on changes in spectra. The Zan effect has been applied in astronomical observations to study cosmic magnetic fields, offering a new perspective for exploring the plasma universe theory. In 1908, a group of American astrophysicists, led by George Ellery Hale, used the Zan effect at the Mount Wilson Observatory to successfully measure the magnetic field of sunspots for the first time. This discovery provided an important data foundation for later astrophysics research. The plasma cosmology theory, which suggests that most celestial bodies have magnetic fields, applies not only to planets but also to stars. However, the magnetic fields of stars are more complex and irregular compared to those of planets. As technology advanced, astronomers gained a deeper understanding of the sun's magnetic field. Surprisingly, they found the sun's magnetic field to be chaotic and disordered, which is completely different from the energy distribution produced by nuclear fusion. If the sun were considered a huge energy source driven by nuclear fusion, its magnetic field should be uniform and stable. However, the reality is that there are magnetic fields of varying strengths on the sun's surface. One hypothesis is that beneath the sun's atmosphere, there are widespread irregular electrical arc discharges, each producing its own magnetic field. This phenomenon could explain the complexity of the sun's magnetic field. Does this provide a strong explanation for plasma cosmology theory? Plasma cosmology theory also offers an explanation for why Earth experiences ice ages. This theory points out that Birkeland currents in the universe are unevenly distributed. When the sun enters an area with weaker currents, the amount of current it absorbs decreases, leading to reduced internal discharge effects and plasma activity. As a result, the energy radiated by the sun significantly decreases, and so does the energy received by Earth, leading to ice ages. Regarding the idea of landing on the sun, what we learned in our childhood tells us that the sun, like many large planets, is primarily made of gas. Based on early observations that the sun's rotational speed varies in different regions, which is inconsistent with the characteristics of a rigid spherical body, it is believed that the sun is a gaseous planet. To achieve the dream of landing on the sun, we may need to reconsider this idea based on a new understanding of the sun according to plasma cosmology theory. According to plasma theory, the sun's energy mainly comes from the dynamic activities of its ionized atmosphere, which means the sun itself doesn't need to maintain a very high temperature. The sun's magnetic and electric fields continuously propagate energy generated in the atmosphere outward, suggesting the surface temperature of the sun could be much lower than previously thought. So, even if the sun's surface temperature is lower, if it is mainly composed of gas, it seems we still can't land on it. But can we conclude this so easily? Previously, most people, including us, believed the sun was mainly made of gas. However, a phenomenon known as solar oscillations, or helioseismology, made us start to rethink this. Helioseismology refers to the vibrations occurring on the sun. Since the launch of the solar observation satellite SOHO in 1995, scientists began detecting solar oscillations. Scientific journals soon reported these findings, including a significant event on July 9, 1996, with a magnitude of 11.3. Further research showed the sun exhibits regular vibrations, shaking approximately every 5 minutes, challenging the conventional understanding that the sun is purely gaseous and generates energy mainly through nuclear fusion. Considering a huge gaseous body, could such regular vibrations occur? Further observations on the sun's internal rotation speeds also provided new insights, pointing towards a possibility. Beneath the sun's dense atmosphere, there might exist a solid core. Regarding the sun's chaotic magnetic field, if the sun were gaseous, its vast and complex magnetic field would cause its shape to be extremely unstable. However, since human records began, the sun has always maintained a stable spherical shape. This further prompts us to consider, if the sun's interior is indeed a rigid solid body, this might contradict the assumption of high temperatures generated by nuclear fusion, as solids cannot exist at temperatures of 15 million degrees. As for whether anyone has actually measured the temperature below the sun's surface, this question has sparked many urban legends about solar exploration. About the temperature of the sun's surface, an intriguing claim was made by a Swedish researcher with experience at NASA. This scholar, who had worked at NASA for 8 years, shared a shocking piece of information with the media. According to him, a measurement in 1998 showed that the sun's surface temperature was only 27 degrees Celsius. This statement sparked widespread debate and skepticism. People wondered, if NASA really had such revolutionary data, why would they choose to keep it secret instead of making it public? The Swedish researcher's explanation was straightforward. He believed that if such information were released, it would challenge our current understanding of the universe, including fundamental theories like relativity. Though this story sounds like an urban legend, Mainly because NASA neither confirmed nor denied these claims, the idea of a cool sun is not new. In fact, scholars have proposed this theory since the 18th century, with one of the most famous proponents being the British astronomer William Herschel, who discovered Uranus in infrared radiation. In physics, the higher the temperature of an object, the greater the total energy it radiates, with an increase in the short-wave components of its spectrum. Generally, when an object's temperature reaches 300 degrees Celsius, it radiates heat mainly in the form of infrared light, invisible to the human eye. As the temperature rises to between 500 and 800 degrees Celsius, the object begins to emit visible light. When the temperature increases further to 1500 degrees Celsius, the object emits white light, which contains a significant amount of short-wave radiation. Regarding the claim that the sun's surface temperature is estimated to be 6,000 degrees Celsius, we once asked our teacher if this means the sun should appear as a bright, slightly blue glowing sphere in the universe. The teacher did not provide a direct answer but hinted that astronauts who have seen the sun in space might offer some insights. Therefore, to truly understand the sun's temperature, one only needs to see it for themselves in space. If you ever get the chance to go to space, don't forget to observe the color of the sun with your own eyes and share your findings with us. Looking back at the journey of exploring the sun, we notice that the United States has initiated the Parker Solar Probe project, which is expected to approach the sun's outer corona layer by 2025. This milestone event is anticipated to unveil many secrets of the sun. Against this backdrop, plasma cosmology theory has attracted widespread attention. This theory not only offers new explanations for the sun's anomalous phenomena, but also provides a novel perspective on the existence of dark matter. The conventional view holds that interactions between celestial bodies are mainly due to gravitational forces. However, when observing the rotation of galaxies, scientists discovered that the rotational speed of celestial bodies at the edges of galaxies far exceeds the predictions of Newtonian gravity. Without the additional gravitational pull from other massive objects, these celestial bodies should theoretically be ejected from the galaxy. Since these bodies remain stable at the edges of galaxies, scientists speculate that an invisible matter, known as dark matter, provides the necessary gravitational force for the outer celestial bodies. Despite the concept of dark matter being proposed in 1922 and several announcements of indirect evidence for its existence by the academic community, direct observation of dark matter has yet to be achieved. In contrast, plasma cosmology theory offers a new approach to explaining the contradiction observed in the rotation of galaxies. The universe is influenced not only by gravity but also by electromagnetic forces due to the existence of Birkeland currents. These forces work together to maintain the stable structure of galaxies. This concept is not widely accepted in the academic community, mainly because it contradicts the Big Bang theory, which describes the universe as expanding from a highly dense point after a massive explosion, gradually evolving into the universe we see today. In contrast, plasma cosmology suggests the universe has always existed in its current state without the need for a Big Bang to explain its formation. Therefore, many scholars are skeptical of this theory, preferring the Big Bang theory. However, this situation is gradually changing. In 2013, observations and analyses of distant gamma-ray bursts using the Swift satellite and the Fermi Gamma-ray Space Telescope revealed a startling discovery, a structure over 10 billion light-years large. This structure, located in the direction of Hercules and Corona Borealis, hence named the Hercules Corona Borealis Great Wall, is the largest known structure in the universe. This finding poses a serious challenge to the Big Bang theory. Considering the universe's age is 13.8 billion years and the Hercules Corona Borealis Great Wall is about 10 billion light-years away from Earth, it means this massive structure formed in just about 3.8 billion years. This challenges our current understanding of the speed at which cosmic structures can form. Therefore, this either implies the existence of an unknown mechanism faster than the speed of light or indicates a fundamental error in our understanding of the universe.